Imagine a future where Mars is no longer a barren desert, but a thriving world teeming with life, where lush forests stretch across its surface, vast lakes shimmer under a breathable sky, and humans call it home. The idea of transforming the red planet into a second Earth isn't just science fiction. It's a bold vision fueled by scientific breakthroughs and our relentless curiosity. Exploring what Mars could become with a genuine atmosphere isn't just about terraforming. It's about unlocking the potential for humanity to step beyond our planet, to settle, to thrive, and perhaps even to ignite a new chapter in our cosmic story. Stay tuned, because the possibilities ahead could redefine what's truly possible for life among the stars. The current state of Mars. Mars is a planet that has fascinated scientists and explorers for centuries, yet its environment remains one of the most extreme in the solar system. Today, the red planet's atmosphere is incredibly thin, with a surface pressure less than 1% of Earth's, composed mostly of carbon dioxide, around 95%. This sparse atmosphere offers little protection from solar radiation and leaves the surface exposed to intense temperature fluctuations, from scorching daytime highs to freezing nighttime lows. Although Mars has some residual weather phenomena, including dust storms that can engulf the entire planet and produce brief, localized weather patterns, it lacks the stable, breathable atmosphere necessary to support human life or complex ecosystems. Geologically, Mars is a world shaped by volcanic activity, ancient riverbeds, and impact craters. Its surface features large volcanoes like Olympus Mons, the tallest volcano in the solar system, and extensive canyon systems such as Valles Marineris. These features suggest that Mars once had abundant liquid water, perhaps lakes and rivers, implying that its climate was once far warmer and thicker with a more substantial atmosphere. Over billions of years, however, Mars lost most of its atmospheric gas to space, a process accelerated by its weak magnetic field and low gravity, which allowed solar wind particles to strip away atmospheric particles. As a result, the planet's surface is now arid, cold, and inhospitable, with a landscape increasingly shaped by dust and rock rather than flowing water. Current efforts to explore Mars aim to understand its atmospheric history and potential habitability. Rovers like Perseverance and Curiosity have drilled into the surface, analyzing soil and rock samples for signs of past life and climate evolution. Satellites orbiting Mars have mapped its mineral composition, revealing clay-rich regions indicative of past water activity, and analyzed atmospheric particles to better understand current weather dynamics. These missions underscore both the scientific intrigue and the practical challenges of future colonization. Mainly, how to create a thick, stable atmosphere or sustain human life amid the existing hostile environment. Looking ahead, imagining Mars with a thicker, more Earth-like atmosphere opens tremendous possibilities. If terraforming efforts succeeded, the planet could shift toward a more temperate climate, with liquid water flowing on its surface again, and a protected atmosphere capable of supporting life. Such a transformation would revolutionize space exploration, potentially turning Mars into a second home for humanity. Current research focuses on bioengineering, atmospheric modifications, and introducing greenhouse gases to kickstart the process. While still in the realm of long-term vision, these ideas carry the promise of turning Mars from a barren desert into a fertile world, full of new opportunities for exploration, settlement, and perhaps even thriving ecosystems someday. The composition of Earth's atmosphere. Earth's atmosphere is a delicate yet dynamic blanket of gases that sustains life, regulates climate, and shields the planet from harmful radiation. Composed predominantly of nitrogen and oxygen, it contains roughly 78% nitrogen, which acts as a buffer to stabilize the atmosphere, and about 21% oxygen, essential for most terrestrial organisms. The remaining 1% includes trace gases like argon, carbon dioxide, neon, helium, methane, and a handful of others. These minor components might seem insignificant, but are vital in maintaining chemical balances, regulating temperature through greenhouse effects, and supporting complex ecosystems. If Mars were to develop an atmosphere similar to Earth's, a significant challenge would be recreating this specific composition. Adding oxygen to support human respiration would require either introducing manufactured supplies or activating in situ resources, such as splitting water ice or melting mineral deposits rich in oxygen. Nitrogen, being inert and vital for maintaining atmospheric stability and pressure, would also need to be freely available in suitable quantities. Achieving about 78% nitrogen would help maintain pressure and prevent the planet from losing gases into space, keeping the atmosphere dense enough to facilitate breathable air and protect against solar winds. The trace gases play a surprisingly powerful role in climate regulation. On Earth, carbon dioxide accounts for approximately 0.4% of the atmosphere, but is crucial as a greenhouse gas, trapping heat and keeping the surface habitable. On Mars, with a thin carbon dioxide-dominated atmosphere now, increasing the volume of greenhouse gases could help maintain surface temperatures suitable for human activity and agriculture. The goal would be to mimic Earth's balanced greenhouse effect without risking runaway warming or destabilization of the atmosphere. Incorporating controlled amounts of methane or other potent greenhouse gases in the terraforming process could give Mars a significant temperature boost, while stable oxygen levels enable complex life support. Exploring the composition of Earth's atmosphere reveals the intricate relationships between its components in climate regulation, biological support, and planetary stability. Replicating this balance on Mars would require meticulous planning, advanced technology, and careful environmental management. Yet, the potential to craft a new world that supports life as we know it remains an exhilarating prospect that pushes the boundaries of science and imagination. With advancements in atmospheric engineering and resource utilization, transforming Mars into a second Earth might yet transition from science fiction into a compelling reality. Imagining an atmosphere on Mars. If Mars suddenly possessed a substantial atmosphere, the implications for the planet's environment and potential for human colonization would be transformative. Currently, Mars's thin atmosphere, composed mostly of carbon dioxide, offers very little insulation or protection from cosmic radiation. Introducing a thicker, breathable blanket of gases could dramatically change surface conditions. Temperatures would likely rise, perhaps making parts of the planet warm enough for liquid water to exist stably on the surface, opening possibilities for establishing lakes or rivers. These bodies of water could serve as crucial resources for both sustaining life and creating a more Earth-like environment, setting the stage for agriculture and long-term habitation. From a scientific perspective, thickening Mars's atmosphere might involve terraforming techniques, such as releasing gases trapped in the polar ice caps, or importing volatile compounds from elsewhere in the solar system. If this process could be managed at scale, it could lead to a greenhouse effect that fosters a more stable climate. Imagine lush, green areas where lush mosses or hardy plants could take root, gradually modifying the atmosphere further through photosynthesis. Over centuries, this could create a self-sustaining biological cycle that enhances atmospheric density and oxygen levels, paving the way for future human settlers to breathe unassisted, grow crops, and establish ecosystems. The prospect of a thicker atmosphere also introduces challenges and opportunities in engineering and safety. Increased pressure and the presence of a protective ozone layer would significantly reduce radiation exposure, making surface activity safer and more practical. Infrastructure development would need to adapt to new atmospheric conditions, a different approach to building foundations, airlocks, and habitats. For colonists, the potential for weather phenomena, such as windstorms or even mild rain, would transform Mars from a barren wasteland into a planet with dynamic weather patterns reminiscent of Earth's, fostering a more familiar environment. The key would be in balancing atmospheric composition to ensure it is supportive without becoming hazardous, such as avoiding runaway greenhouse effects or toxic buildup. Finally, envisioning Mars with a breathable atmosphere sparks a broader conversation about planetary stewardship and ethical considerations. As humanity works toward terraforming, it becomes less about conquest and more about coexistence with the planet itself. The push would be to create a habitable zone that respects the resilience of Martian ecosystems and minimizes disturbances to potential indigenous microbial life. That balance between technological ambition and ecological responsibility could forge a future where Mars isn't just a distant outpost, but a true second home, one that fosters exploration, innovation, and perhaps a new chapter in human history. Potential sources of Martian atmosphere. Mars' atmosphere today is a thin, tenuous layer composed mostly of carbon dioxide, with traces of nitrogen and argon. This scarcity results from billions of years of solar wind stripping away lighter gases, leaving behind a barren, Mars-appropriate environment. But the idea of restoring or augmenting its atmosphere hinges on understanding plausible sources that could supply or replenish these gases. One natural source is the planet's own interior. Volcanic activity, for example, may have released vast quantities of gases in the distant past, including carbon dioxide, water vapor, and sulfur compounds. While geological activity on Mars has waned considerably, inducing or mimicking such processes artificially could become a viable method to add atmosphere over time. Another promising source lies beyond Mars itself, importing gases from nearby celestial bodies. The Moon's volcanic history, albeit limited compared to Earth, managed to release some gases that could, in theory, be harvested and processed for future use. More practically, asteroid mining presents intriguing possibilities. Certain asteroids contain hydrated minerals and volatile-rich compounds, especially carbonaceous chondrites. These contain substantial amounts of water ice as well as complex organic molecules, which could be extracted and subsequently broken down into oxygen and hydrogen, key building blocks for breathable atmospheres. Advanced robotic systems could facilitate the collection and delivery of these materials, making them an ongoing supply chain for atmospheric regeneration. Human intervention itself could play a significant role in creating or stabilizing an atmosphere. In terraforming scenarios, humans could introduce greenhouse gases like methane or even chlorofluorocarbons, synthetically produced gases that are effective at trapping heat. Controlled release of these gases would thicken the atmosphere and begin a feedback loop of warming, causing more volatile compounds to be released from the soil and ice caps. Additionally, genetically engineered microorganisms could someday be designed to survive in extreme environments and produce atmospheric gases through metabolic processes, gradually increasing atmospheric pressure and composition. Over the long term, a combined approach, leveraging planetary geology, extraterrestrial resource extraction, and bioengineering, could transform Mars into a more Earth-like world capable of supporting human colonization with a sustainable, self-maintaining atmosphere. This entire vision relies on a complex interplay of science, engineering, and imagination, but each step makes the goal of a breathable, life-supporting Mars more plausible. As technology advances, the idea of harnessing these diverse sources to rebuild or enhance the Martian atmosphere transitions from science fiction to a tangible pathway toward our future among the stars. Effects on Martian climate and weather. If Mars possessed a substantial atmosphere, the planet's climate and weather patterns could shift dramatically, transforming from the barren desert landscape we are familiar with into a dynamically active environment. The thin carbon dioxide-rich atmosphere that currently exists on Mars contributes to extreme temperature fluctuations, scorching daytime highs and frigid nights. Introduce enough atmospheric pressure and greenhouse gases, and Mars could develop a more stable thermal equilibrium. Temperatures would likely become less punishingly extreme, allowing for a broader range of liquid water stability, and offering a hospitable environment for diverse weather phenomena. With an atmosphere thick enough to trap heat, storms could become commonplace, creating a climate reminiscent of Earth's more temperate zones. Dust storms, already occasional on Mars, could escalate into vast, planet-wide events that blanket the entire surface in red haze. Such storms would dramatically influence temperature distribution, potentially redistributing heat and moisture across the planet. Unlike Mars' current static sky, a thicker atmosphere would support the development of cloud systems, potentially water or even sulfuric acid clouds, depending on the composition of gases released through terraforming. These clouds would create variability in sunlight reaching the surface, further influencing local weather patterns, from rainfall to snowfall in the polar regions. The cycle of precipitation might emerge if water vapor levels rise sufficiently, enabling rivers, lakes, and maybe even small seas to persist for longer periods. If human colonization becomes a reality, managing seasonal shifts would become part of daily life, much as it is on Earth. Weather systems could be driven by temperature gradients created by the atmosphere's interactions with the soil surface, generating wind belts and storm fronts. These wind patterns might also aid in distributing atmospheric gases evenly across the planet, gradually stabilizing the climate and creating more predictable weather over time. Extended periods of rainfall could break the planet's dusty, dry reputation, and eventual terraforming projects might harness weather cycles to cultivate a sustainable, Earth-like environment. Envisioning the planet with an active climate system sparks potential for expanding life beyond Earth. It would facilitate the development of biospheres capable of supporting terrestrial organisms, which in turn could modify the atmosphere further, creating even more complex weather patterns. Human settlements, powered by sustainable energy sources, could adapt to these new climates, possibly utilizing advanced weather forecasting systems. Ultimately, a thicker atmosphere on Mars could turn its once hostile environment into a place where weather becomes an element of daily life, shaping landscapes, influencing agriculture, and fostering a growing sense of familiarity in a world that was once almost entirely alien. Impacts on surface geology and surface processes. The presence of a substantial atmosphere on Mars would significantly reshape its surface geology, initiating an entirely different suite of surface processes. Without the relentless bombardment of solar wind stripping away atmospheric particles as in the current thin state, weathering and erosion dynamics would shift dramatically. Wind-driven processes, in particular, would become dominant, leading to the formation of vast dunes and rippled terrains that subtly mask older geological features. Over time, these wind-blown sediments could bury and preserve ancient volcanic structures and impact craters, creating a layered record that documents Mars' evolving climate and surface history. The thicker atmosphere would also encourage chemical weathering, which is minimal on today's Martian surface due to scarce water and low temperatures. Increased atmospheric pressure and temperature fluctuations would cause minerals to react with water vapor and other gases, gradually altering the crustal composition. Iron-rich minerals might develop distinctive rust-colored coatings, but contrasts between different geological units could become more subdued, blending ancient volcanic rocks with sedimentary deposits. Such processes could smooth out sharp features, leading to a more subdued landscape akin to Earth's deserts, but with a uniquely Martian signature of layered sediments and mineralized regions. Surface processes would incorporate new kinds of geological activity, resulting from interactions between the atmosphere, surface, and subsurface. The presence of a denser atmosphere might facilitate the development of transient liquid water pockets during warmer periods, promoting localized melting and erosion. This could even trigger episodic landslides on steep crater walls, or the erosion of volcanic edifices, reshaping the terrain more actively than it currently does. Impact craters might also be modified over time, as falling particles and chemical weathering soften ejecta blankets and fill craters with sediments, gradually reducing their sharpness and visibility. A warming climate driven by a thicker atmosphere could spark extensive volcanic and geyser activity, further modifying the surface. Magmatic movements might be influenced by changing pressure conditions, leading to eruptions that deposit new lava flows or volcanic ash layers, creating fresh geological features. Hydrothermal processes, if sustained, could forge mineral-rich deposits and alter the mineralogy of existing terrains. Ultimately, an atmospheric presence would transform Mars from a static, heavily cratered world to a geologically active one, with ongoing surface reshaping, sedimentation, and chemical alteration paving the way for a dynamic planet that could support evolving ecosystems and human settlements. Possibilities for liquid water stability. If Mars were to develop a thicker atmosphere, rich in greenhouse gases, the potential for liquid water to exist on its surface would dramatically increase. Without a substantial atmosphere, any liquid water would rapidly evaporate or freeze due to the intense radiation and low pressure. However, with an atmosphere thick enough to trap heat and maintain moderate pressure, liquid water could find refuge in stable environments. Imagine vast plains, where water flows intermittently or exists in persistent ponds and lakes, fed by melting ice caps or underground aquifers. This creates a potential for ecosystems to develop, even if microbial life were the only future inhabitants. The stability of liquid water depends heavily on local conditions and the precise composition of the atmosphere. For instance, a significant increase in carbon dioxide levels would enhance greenhouse effects, similar to Earth's early atmosphere, raising surface temperatures sufficiently to permit stable surface water. Regions near the equator could see seasonal, or even perennial lakes, with water remaining liquid during warm periods and freezing during colder intervals. Subsurface aquifers might also act as reservoirs, providing a consistent source of liquid water protected from atmospheric fluctuations. Such underground reservoirs could enable future colonists to access water for drinking, agriculture, and industrial processes, even if surface conditions remain harsh. Furthermore, the presence of liquid water could foster the development of complex climate systems. Ocean-like bodies could distribute heat across the planet, moderating temperature swings and creating more hospitable zones. In this scenario, coastal areas might experience relatively mild climates, supporting plant and microbial life. Over time, the atmospheric composition could stabilize through biological activity or even terraforming efforts, gradually maintaining surface water and creating a self-sustaining cycle. This progress preserves the optimistic vision of Mars transforming from a barren desert into a thriving world, with stable liquid water acting as the heart of its evolving climate. Finally, envisioning long-term habitation, the continued existence of liquid water would be instrumental in establishing a sustainable human presence. Water is vital not only for drinking but also as a raw material for creating oxygen and hydrogen through electrolysis, fueling spacecraft, or powering habitats. With appropriate technological advancements, humans could manage and manipulate water sources, bringing ice from the poles or melting underground reserves. Such control could stabilize local environments, allowing agriculture to flourish and support the development of a Martian biosphere. In essence, an atmosphere conducive to stable liquid water opens enormous possibilities for terraforming and human colonization, making Mars a more Earth-like and welcoming world. The potential for supporting life. If Mars harbored a thicker, more stable atmosphere, the possibilities for life would transform dramatically. The presence of an atmosphere capable of supporting liquid water on the surface would create a delicate balance that might enable microbial life to thrive. Currently, Mars' thin atmosphere, composed mostly of carbon dioxide, is insufficient to retain heat or trap enough solar radiation to sustain stable liquid water, which is fundamental for life as we understand it. However, with a thicker atmosphere, the surface temperature could increase sufficiently to allow for the persistence of water in liquid form, forming small lakes, ponds, or even rivers in regions that now appear barren. This environment would open new avenues for biological possibilities. Microorganisms, particularly extremophiles similar to those found in Earth's harshest environments, could potentially colonize the surface or subsurface. Imagine bacteria that utilize sulfates or other inorganic compounds as energy sources, thriving in the mineral-rich soils, or algae forming tiny, localized ecosystems in moist cracks or subsurface aquifers. If Earth's history offers any analogy, the presence of a stable atmosphere and liquid water dramatically increases the likelihood of life originating or migrating to that planet, making Mars a prime candidate for microbial colonization. From a terraforming standpoint, a thicker atmosphere also suggests the potential for developing a more breathable environment over time. Human colonization would become increasingly feasible in these conditions, with the possibility of growing crops, cultivating soil, and establishing sustainable settlements. Technologies like greenhouse domes could harness the increased atmospheric pressure and warmth to grow food with less energy expenditure. Over several centuries, this could lead to a self-sustaining ecosystem, gradually transforming Mars into a more Earth-like habitat. The presence of an atmosphere capable of supporting life would markedly reduce the challenges associated with protecting humans from radiation and extreme temperature fluctuations, making long-term habitation more realistic. The idea of Mars supporting life hinges on the continued development and management of its atmospheric composition. Initiatives such as releasing greenhouse gases to trap more heat, or importing volatile compounds from comets or asteroids, become more appealing in a scenario where the atmosphere already provides a foundation for sustaining water and warmth. It ignites the possibility that, with enough technological ingenuity, Mars could ultimately host a vibrant, biodiverse biosphere, an extension of Earth's life, adapted to a new world. This vision, infused with optimism, invites us to consider that Mars might one day be more than a barren planet. It could become a new frontier teeming with life, both microbial and perhaps even more complex. Human habitation and colonization prospects. If Mars were to develop a substantial, breathable atmosphere, the prospects for human habitation and colonization would shift dramatically. Current challenges, mainly the planet's thin atmosphere composed mostly of carbon dioxide, pose severe obstacles for life as we know it. But with an atmosphere rich in oxygen and nitrogen, the initial barriers to establishing a sustainable human presence would be substantially lowered. Construction of habitats could transition from complex life support systems, which currently require extensive energy and resources to maintain, to more natural conditions that support human respiratory needs without massive filtration. Once the atmosphere becomes comparable to Earth's, several key advantages emerge. Imagine vast open-air settlements rather than cramped domes or underground modules. Agriculture would become more feasible on a large scale. Plants could thrive outdoors, harnessing natural sunlight, and bestowing additional oxygen into the environment. This could trigger a positive feedback loop for terraforming efforts, gradually improving the climate and making the planet more hospitable over generations. Human activity could then resemble colonization on Earth, with cities sprawling across the landscape, connected by roads and agriculture extending into the horizon. Safety and health also improve significantly. Reduced reliance on life support systems minimizes logistical complexity and costs, lowering the barrier for long-term colonization. Breathing fresh air, exercising outdoors, and enjoying natural sunlight would improve mental well-being, crucial for maintaining motivation and resilience over extended periods away from Earth. The presence of a more substantial atmosphere would also act as a natural protector against some space radiation, although additional shielding would still be needed. Still, the idea of a planet with an atmosphere capable of supporting human life resoundingly enhances the feasibility of establishing a self-sustaining society on Mars. The challenges of terraforming and atmosphere enhancement remain daunting, but recent advances in planetary science and environmental engineering fuel optimism. Technologies such as releasing greenhouse gases to trap heat and thickening the atmosphere through engineered planet-wide processes are under serious consideration. In a future where Mars sported a substantially thicker, breathable atmosphere, the dream of an off-world Earth-like environment would become much less science fiction and much more achievable reality. Human explorers and settlers could then justifiably view Mars not as a barren frontier, but as a new world on which to build a future, with all the possibilities that come with a functioning, life-supporting atmosphere. Environmental challenges and hazards. A thick, breathable atmosphere on Mars would undoubtedly transform the landscape into a more hospitable place for humans, but it also introduces a host of environmental hazards that demand careful consideration. One of the most immediate concerns is the presence of potentially harmful gases. Even with a carefully managed atmosphere, residual traces of planet-wide gases like carbon dioxide, methane, or even trace amounts of other volatile compounds could pose risks. In some scenarios, microbial life or geological processes might produce methane, which if accumulated, could lead to unpredictable fire or explosion hazards, especially in confined habitats. Another challenge lies in the increased risk of dust storms, which could become even more intense and persistent with a thicker atmosphere. These storms, driven by temperature differences and surface winds, could blanket large areas of the planet, reducing visibility to near zero and clogging machinery, solar panels, and ventilation systems. Such storms are a staple of current Mars weather patterns, and adding an atmosphere with more density and moisture could intensify their severity. This not only hampers exploration efforts, but also impacts the structural integrity of habitats, which would need reinforced designs and emergency protocols to counteract dust infiltration and sudden storm surges. Radiation remains one of the most daunting hazards, regardless of atmospheric alterations. While a denser atmosphere would provide some shielding from cosmic rays and solar radiation, it might not be enough for long-term human habitation without additional protective measures. The atmosphere would still be mostly thin compared to Earth's, so surface radiation levels could remain dangerously high, necessitating habitat structures with specialized shielding, possibly using regolith, water, or other materials, to ensure safety. This poses logistical and technological challenges, but also offers an opportunity to innovate in habitat design. Lastly, A thicker atmosphere could lead to climatic extremes that are challenging to predict or control. Increased atmospheric pressure could cause local weather phenomena, such as sudden temperature swings, unexpected storms, or even localized rainfall if water vapor is present. While rain on Mars remains purely speculative in many terraforming models, any introduction of moisture-bearing atmosphere inherently risks unpredictable weather patterns that could threaten both human life and colonization infrastructure. Navigating these hazards would require a combination of advanced forecasting capabilities and adaptive engineering solutions, ensuring that settlers are prepared for the planet's potentially volatile environment. Technological and terraforming innovations. If Mars were to be endowed with a substantial atmosphere, the scope of technological innovation and terraforming might shift from speculative to increasingly tangible. The primary challenge would be creating a self-sustaining environment capable of supporting human life while maintaining atmospheric stability over centuries. One of the most promising pathways involves advanced greenhouse gas production combined with biological enhancements. Technologies could deploy large-scale factories or orbital solar mirrors that actively convert local regolith and ice deposits into greenhouse gases like methane and nitrogen, gradually thickening the atmosphere and trapping heat. These measures would mimic natural processes, but on an engineered scale, providing the necessary insulation without relying solely on slow planetary processes. Microbial and plant-based terraforming could accelerate atmospheric regeneration and stabilization. Researchers imagine specially engineered microorganisms designed to flourish in the harsh Martian environment, capable of fixing nitrogen and producing oxygen through photosynthesis. These life forms might be deployed in layered biospheres or specially constructed greenhouses initially, with the goal of gradually spreading their benefits across the planet. Advances in genetic engineering, such as CRISPR, could allow scientists to develop organisms optimized for low-pressure, high-radiation conditions, effectively turning parts of Mars into biological factories. Over time, as these ecosystems expand, they could produce vital atmospheric components sustainably, reducing dependence on continuous human intervention. On the technological front, orbital infrastructure would play a critical role. Large spacecraft or orbital stations equipped with climate control systems could regulate temperature, atmospheric composition, and even weather patterns on a planetary scale. Similar to Earth's cloud seeding or climate engineering efforts, Mars could someday benefit from advanced aerosol dissemination systems that help seed clouds and trigger precipitation, promoting the formation of stable water cycles. This would be paired with surface-based systems, massive domes or inflatable habitats, that serve both as research stations and as seedbeds for terraforming experiments. Coupled with AI-driven monitoring, these technologies could adapt dynamically to changing conditions during the terraforming process, optimizing resource use and ensuring planetary safety. In combination, these innovations could transform Mars into a more hospitable world within a human lifetime. The fusion of cutting-edge biotechnologies, planetary engineering, and orbital infrastructure creates a virtuous cycle, where each step facilitates the next. The ultimate vision is to develop not just a livable environment, but a dynamic, resilient ecosystem capable of supporting human populations with minimal ongoing intervention. While the technical hurdles are immense, the potential for collective ingenuity and perseverance makes this goal an inspiring horizon, turning the red planet into a vibrant, new frontier of life. Ethical and planetary preservation considerations. Contemplating the idea of introducing an atmosphere to Mars naturally sparks complex questions about the morality of altering a celestial body that might harbor its own form of primordial existence, however sparse or microbial that might be. The impulse to terraform stems from a desire to expand human horizons, to make new worlds habitable for future generations. Yet it raises the fundamental issue of whether humanity has the right to impose its will upon a planet that's been isolated in the cosmos for billions of years. Before initiating any large-scale atmospheric modifications, a conversation about planetary stewardship becomes essential, considering whether Western notions of progress and colonization are ethically compatible with preserving the intrinsic nature of other worlds. The act of thickening Mars's atmosphere isn't just a technical challenge, it is a moral one. Many argue that planetary engineering would constitute a form of contamination, disturbing environments that might be considered unique ecosystems, even if they are not yet fully understood. While some advocate for a cautious approach that prioritizes Mars's scientific integrity, others believe that human intervention could coexist with a sense of respect and responsibility. These considerations remind humans to evaluate the long-term consequences of their actions, including how terraforming might impact potential microbial life forms that could exist beneath the surface or in briny aquifers. The risk of accidentally disrupting or destroying any native life, however microbially simple, is a concern rooted in planetary ethics that refuse to ignore the intrinsic value of potential extraterrestrial ecosystems. Moreover, there's the question of whether terraforming Mars aligns with broader planetary preservation principles. If humankind invests colossal resources into transforming the red planet, it could divert attention and funding from Earth's urgent environmental crises. This creates a moral dilemma. Should efforts focus on healing and protecting our homeworld first, or is it justified to expand outward as a form of moral exploration and responsibility? Some argue that spreading humanity across multiple worlds acts as a safeguard for civilization, an insurance policy against planetary catastrophes. Yet this carries the risk of repeating colonial paradigms that have historically led to exploitation and cultural erasure. Balancing the aspirational goal of making Mars livable with a genuine commitment to planetary preservation demands careful, reflective planning that privileges sustainability and respect. In the end, the ethical considerations surrounding the creation of an atmosphere on Mars hinge on human humility and recognition of limits. The technological prowess to modify planets exists, but with it comes a moral obligation to proceed thoughtfully. Developing international consensus, perhaps through organizations akin to the United Nations, would help guide these efforts, establishing rules that emphasize respect, conservation, and shared responsibility. If humanity proceeds with an awareness of its moral weight, the endeavor can transcend mere conquest, evolving into a mature act of planetary stewardship where caution, curiosity, and respect for extraterrestrial environments are balanced in pursuit of a future that honors the universality of life and the uniqueness of each celestial body. Martian atmosphere and its influence on solar system dynamics. If Mars had a thick Earth-like atmosphere, the ripples would extend far beyond its surface, subtly nudging the entire solar system's dynamics. Currently, Mars' thin atmosphere, composed mostly of carbon dioxide, has a negligible effect on gravitational interactions or orbital mechanics. But imagine this modest climate shift, where Mars' atmosphere becomes dense enough to influence solar radiation absorption, thermal emissions, and even asteroid-meteorite interactions. Such a transformation could impact how solar energy is distributed across the system. Increased atmospheric density would cause Mars to retain more heat, potentially leading to a shift in its orbital eccentricity over long timescales, due to complex gravitational resonances. While these effects wouldn't dramatically destabilize the orbits of planets, they could tweak subtle gravitational interactions, especially in the asteroid belt. The presence of a dense atmosphere might also modify the way Mars interacts with solar wind and magnetic fields, especially if the atmosphere gets in contact with a developing magnetosphere. A thicker atmosphere would act as a shield, somewhat like Earth's, reducing atmospheric stripping by solar wind particles. This protective effect might lead to a modest increase in Mars' mass over geological timescales, which could precisely influence nearby celestial bodies through gravitational tugging. The interplanetary dust and debris particles are more likely to settle or burn up in such an environment, potentially changing the frequency and impact of meteor strikes, further influencing ring dynamics and space weather in Mars' neighborhood. Terraforming efforts, fueled by advanced technology, could also establish a self-sustaining Martian climate, further influencing planetary system variability. As humans and automated probes start modifying the atmosphere, greenhouse gases could trap more solar energy locally, raising temperature and maintaining atmospheric pressure suitable for life. This change would result in more stable conditions for human colonies, but also affect the local mass distribution slightly, creating small but meaningful shifts in Mars' gravitational influence on nearby bodies. The influence on asteroid trajectories, for example, might become more predictable over time, leading to improved asteroid deflection strategies and space traffic management in Mars' vicinity. All these potential modifications could inspire a new perspective on how planetary atmospheres, even if minuscule in size, can ripple outward into the cosmic dance that unites the solar system. With a breathable, substantial atmosphere, Mars could become a hub that subtly alters the gravitational ballet of planets, moons, and smaller objects, reminding us that atmosphere isn't just a planetary feature, but a keystone in the broader dynamics that tie the solar system together. As we move toward terraforming, understanding these effects invites a future where Mars isn't just a dormant rock, but an active participant in celestial choreography, shaping the evolution of the entire system. Long-term evolution and stability of a Mars atmosphere. A stable, long-lasting atmosphere on Mars would transform the planet's future from a fragile, inhospitable world into one capable of sustaining substantial human activity and life. For this to happen, the atmosphere would need to resist disintegration and escape into space over geological epochs. Mars' current thin atmosphere is primarily due to its weak gravity and lack of a global magnetic field, which allows solar wind particles to strip away atmospheric gases continuously. Achieving atmospheric stability would require addressing these fundamental issues, either by thickening the atmosphere significantly or by developing protective technological measures. In a scenario where Mars manages to retain a substantial atmosphere over millions of years, processes such as volcanic outgassing could play a crucial role in replenishing atmospheric gases. Volcanic activity, if reactivated or artificially stimulated, might release CO2, nitrogen, and water vapor, gradually thickening the atmosphere. This would create a positive feedback loop where increased atmospheric pressure and temperature could further stimulate volcanic activity and the release of greenhouse gases, leading to a warming trend that stabilizes and sustains a denser atmosphere. However, without active sources of replenishment, the atmospheric gases would gradually escape, especially lighter molecules like hydrogen and helium, leaving behind heavier molecules such as CO2, which could still sustain a greenhouse effect over long periods. A key challenge for the long-term stability of a terraformed Mars involves protecting the atmosphere from solar and cosmic erosion. One theoretical solution is the deployment of magnetic shields or artificial magnetic fields around Mars, which could deflect the solar wind and reduce atmospheric stripping. This concept, while ambitious, has gained attention in advanced colonization plans, as it could help maintain atmospheric integrity over centuries or millennia. Additionally, creating a climate stability mechanism, such as a planetary-scale greenhouse, would help regulate temperature fluctuations and prevent atmospheric collapse during colder periods. Careful balancing of greenhouse gases and continuous monitoring would be essential, making terraforming a gradual but potentially sustainable endeavor. Over extended timescales, the evolution of the Martian atmosphere might also include the development of complex weather patterns and water cycles, which would influence the stability and composition of the atmosphere. If water bodies form, their interactions with atmospheric gases would create a dynamic equilibrium, fostering a richer, more Earth-like environment. While the processes involved would be intricate and require technological support, the prospects of managing and maintaining a stable atmosphere on Mars grow brighter with ongoing advancements in planetary science, atmospheric engineering, and climate regulation. Such developments could ultimately unlock the door to permanent human presence, transforming Mars from a frozen desert into a new home that endures through the ages. If Mars had a substantial atmosphere, the planet's surface conditions would transform dramatically, shifting from a barren desert into a more Earth-like environment capable of supporting a range of life and human activities. Today, Mars's thin atmosphere, composed mostly of carbon dioxide, has a surface pressure less than 1% of Earth's, resulting in extreme temperatures, little protection from cosmic radiation, and the absence of weather systems capable of redistributing heat. Introducing a thick, breathable atmosphere, envisioned as part of a comprehensive terraforming effort, would mean creating a protective blanket around the planet, allowing for water stability on the surface, and supporting a wider variety of ecosystems and human settlements. One immediate consequence of a denser atmosphere would be the stabilization of temperatures. The current climate varies wildly, with surface temperatures often plunging well below freezing. A thicker atmosphere would trap more heat through a greenhouse effect, even before introducing additional gases like water vapor or oxygen. This could maintain more moderate temperatures, making agricultural development feasible and encouraging the longevity of liquid water on the surface. For example, with a sufficient greenhouse effect, regions near the equator could sustain rolling green landscapes, allowing crops to grow without reliance on advanced indoor farming. This would be a major step toward establishing self-sustaining colonies and reducing dependency on imports from Earth. The composition of Mars's atmosphere would need to be tailored to support human life directly, especially with oxygen levels high enough to allow breathing without cumbersome oxygen tanks. Achieving this involves not only thickening the atmosphere but also introducing organisms capable of photosynthesis, such as algae or certain bacteria, to convert carbon dioxide into oxygen. Over time, these biological agents could establish a balanced, breathable atmosphere, resembling Earth's more closely. Such a process would likely take centuries, but the cumulative effect would significantly improve the habitability of the surface by enabling more natural life support systems, reducing the reliance on technology-heavy habitats and encouraging open habitats in the long run. There are still substantial challenges, of course. The planet's low gravity, roughly 38% of Earth's, would influence atmospheric retention. A thicker atmosphere could gradually be lost to space if not properly stabilized, especially with the weak magnetic field Mars currently has. Implementing magnetic shields or other protective measures might become necessary to prevent atmospheric erosion. Nonetheless, with advanced engineering and biological terraforming techniques, these hurdles could be overcome. The prospect of a Martian surface with a stable, life-supporting atmosphere ignites the imagination. A true second chance for planetary colonization, and a new chapter in humanity's quest to expand beyond Earth. Imagine a Mars transformed into a thriving world, where a breathable atmosphere sparks life, green landscapes, and bustling human colonies. We've seen how adding even a thin atmosphere could warm the planet, support water cycles, and pave the way for agriculture and settlements. The idea of terraforming Mars isn't just science fiction anymore. It's a tantalizing possibility that could redefine humanity's future among the stars. Thanks for joining us on this journey to rethink what could be. Your curiosity fuels exploration, and together, we're inching closer to turning sci-fi dreams into real-world endeavors. If you're as excited as First am about the future of Mars and space colonization, hit that subscribe button. You won't want to miss the groundbreaking projects and discoveries ahead. Stay tuned for more insights, future missions, and bold ideas about our cosmic adventures. The Red Planet might just become our next home someday, and the adventure is only beginning.